This is lesson 4.8 from Algebra 2, and we are continuing our exploration of transformations of trig functions. Today we're going to talk translations. Okay, so now we're shifting left, right, up, down. We're not changing the size or the shape of our graph. We're just moving it around. So there is one term here that you're going to have to be familiar with, and that's a phase shift. Trig graphs get their own special name for horizontal translations. Okay, so anytime I'm sliding left or right, we refer to it as a phase shift. And part of the reason for that, and you're going to see this as we move through the lesson, but part of the reason for that is these functions are cyclic, okay? They cycle over and over again. They're periodic, which means that I can actually establish the same effect by moving to the right as I can by moving to the left. Now, it might be different quantities that I'm moving left and right, but I can make the graph look the same by shifting it left or right. And so that can muddy things up a little bit when we talk about horizontal translations because they're not unique, okay? I could give you a picture of a graph and someone could say, oh, I would move that to the left by this much, and someone else would say I would move to the right by this much, and you both could be correct. So that's why we give it a different term here. Vertically, we just still refer to it as a vertical translation or a vertical shift. Okay, so these things come from translation rules. So translation rules look like this. They involve addition and subtraction. So we're going to be adding something to the x, we're going to be adding something to the y, or subtracting. Okay, and remember that this will be like this will give you the phase shift. Right or left. This gives you the vertical shift. So I think this is actually can be a little bit more straightforward than the one that was dealing with like the period and the amplitude. So when I look at example 1 here, I've got a sine function, okay? And it just says identify the phase shift. Now what you have to remember is this is the equation. The equation is backwards from the rule. If I was to write my rule for this, it would look something like x minus 2 pi over 3. Now, as far as my y value goes, which is this here, I don't see anything added or subtracted from it. And keep in mind, remember we talked with the amplitude about how we usually take the y numbers and move them over to the right. That's also true with your vertical shifts. And so a lot of the times that vertical shift number will actually be tacked down here at the end, like it got moved over from the y side. I don't see that here either though, so there is no vertical shift here. So the question here is just saying, what is the phase shift? The phase shift comes from this, and I would say that my phase shift is 2 pi over 3 to the left because it is subtracting. So the effect of this thing would be to take all of my points and shift them by 2 pi over 3 to the left. Okay, so example 2, I'm giving you a translation. I've got a phase shift of positive pi, meaning we're moving pi to the right, and a vertical shift of negative 2, which is moving down. Okay, we're going to write an equation for this image. So the original equation they're telling us to use is sine of x. And remember, these things are going to go in opposite from what they look like in the rule. So with my x, and I'm going to write it kind of ugly up here, and then we'll write it nice down at the bottom. With my x, I'm going to put in a minus pi, because I'm doing the opposite of what the rule says. And with the y, I'm putting in a plus 2. Now, what's going to happen here is this plus 2 is going to get moved to the other side. We're going to subtract it from the other side. So my final equation would look like this. Sine of, in parentheses, x minus pi. And those parentheses are important to show that the minus pi belongs to the x. And then our minus 2 would be hanging on down here at the end. So it was originally a plus 2, and then I subtracted it and moved it over here. I want to remind you of what we said when we started this example. We said that this would move pi to the right and 2 units down. That just came from my rule. That came from this. We're going to need that when we go to sketch this graph. So that's why I wanted to remind you of what we said and write it down so that you would remember. So this graph here is the original sine function. Again, I can tell that because it starts at 0, 0. It's got an amplitude of 1. And what I'm going to do to these points is move them all by this much. So I'm going to take everything and shift it over to the right by pi and then move it down by 2. Okay? So start with 0, 0. This point is going to shift to the right by pi. So now it's going to be here. And then it's going to be moved down 2 units, which actually the way this is numbered, 2 units would be here. Okay, so my 0, 0 moved down here. Let's take my maximum point. So I'm kind of working through my critical points. I'm doing this point. Okay, next up I'm going to take this point, which right now is at pi over 2. So if I do pi over 2 plus 1 pi, I want you to think about that for a second. That's like 1/2 plus 1 in terms of pi. So 1/2 plus 1 is 1.5, otherwise known as 3 pi over 2. Okay, so this point is going to shift pi to the right and down 2 units. Now right now it's at positive 1. So down 2 units would be here and then here. So this is now my new maximum. Okay, I'm going to run out of colors here, but I'm going to try to keep up as long as I can. Oh, let's see. What other colors can I come up with? We'll do a purple and hopefully that'll look different from a blue. Okay, so now my pi is going to shift to the right by pi. So that's now going to be at 2 pi, and it's going to shift down 2 units. So 1, 2, and it's going to be here. Okay. My 3 pi over 2, which is this point here, is going to shift to the right by pi. So 3 over 2 plus 1 pi would take me to 5 over 2. And then I'm going to go down 2 units from here. This is actually going to take me off the graph. I'm a little annoyed with myself that I didn't make my graph larger, but down 2 units would take me here. Okay, so far, and then my next point would end up over here someplace. So my one cycle of the graph is going to look like this. Okay, I've shifted this portion of the graph to the right by pi and down by 2. And this is where it ended up. Now, I certainly could go back and, fill in the rest of these points. I could say, okay, I know that means there's going to be a low point here. There's going to be a midpoint here. There's going to be a high point here, back at the axis here. And so this is what my function is going to look like. Anytime I ask you to draw one of these, I'm concerned with seeing one full cycle. So as long as your graph shows me one full cycle of your transformed function, you're good to go. Okay, you don't have to transform the entire thing. If you can transform one cycle, I know you can transform the rest of it. Okay? Okay. Whoops, didn't mean to do that. Sorry, I actually meant to flip my page. Ooh, a tangent function. I haven't gotten to do one of these yet. Okay. Tangent function. You're not going to be working with tangent very often. Quite honestly, it's going to be almost always sine and cosine, but we can do this. The tangent function, we know typically goes through the point 0, 0. Usually our tan function comes up like this and then curves like that. Okay, so what's happened here is my tangent function, this point has now shifted over here to the left. Okay, and so what I'm seeing is a shift to the left by, let's see, if this is negative pi over 2, this would be negative pi over 4. So as far as a rule here, I would say that my translation took my x values and shifted them to the left by pi over 4. I'm not seeing a vertical shift here, and I know this point is kind of highlighted for you. That's just highlighted because it's a y-intercept, but the curve of my function didn't change anywhere. This curve is usually what happens right over the x-axis. So I didn't shift up or down at all here. I just shifted to the left by pi over 4. So when I go to write my my equation for that, I would say y equals tangent of x plus pi over 4. Because remember, in your equation, it's opposite. So that'd be it for this question. But I want to propose something to you. I just kind of jumped in and started telling you what to do and expected that you would all believe me. But did anyone stop to question me at all? Sometimes you should. Sometimes you should question me. Because, yes, this would be where my parent function went through, the origin. Okay, it would go right through the origin. But what if I, instead of shifting to the left, what if I shifted to the right instead? Isn't it possible that I took this and shifted it this way? Okay, so just so we're clear, this is like 2 pi over 4 is the same as pi over 2. And this is 4 pi over 4. So halfway between those two, this point here would be 3 pi over 4. So someone, somewhere, could have said, wait a second, I disagree with what Mrs. Trigno is saying. I think this is a translation of positive 3 pi over 4. Oh, yeah, that would be my rule. Sorry, I left out the comma y. And then they would have written their equation as y equals tangent of x minus 3 pi over 4. And you know what I would say to this person? I would say they're right too. Okay, this function and this function are going to look exactly the same because of that periodic piece, that piece where the graphs repeat themselves. If you wanted to, you could make the claim that I took this point and moved it all the way over here. I mean, we could figure out what this point is and say I did a translation by that much and write that function, and that would work too. Okay, so these things are not unique, and anytime things are not unique, they're more complicated. Okay, they can be more confusing. Just to make sure I convince you, let's pull up a Desmos graph here. Get rid of this one from the last lesson. Okay, so just to remind you real quick, here's the original tangent graph. Okay, that's what the original tangent of x looks like. I think I'm going to make that a dotted line so you know it's the parent function. And we'll do that. Okay. Actually, I'm going to make it boring and dotted. If I typed in the first function that we came up with, that'd be y equals tangent of x plus pi over 4. You'll notice that we took this from the origin. Where's my origin here? Sorry, my graph is shifted way over. Here's my origin, okay? And it shifted to the left by pi over 4, okay? So that's the new function that I'm looking at. But if I typed in the second one we came up with, y equals tangent of x minus 3 pi over 4, it's going to land in the exact same place. So the blue graph and the green graph are exactly the same, okay? Because one shifted to the left and one shifted to the right, but they landed right on top of each other because it's periodic, because it repeats itself over and over again. So this green graph, technically what I did is I took this 0, 0, and I shifted it over to here, okay? But that made it so that it lined up with the x plus pi over 4 as well. Okay, I hope you're convinced. I think you're probably convinced. And many of you are probably willing to just believe me anyway, which I appreciate, but really, you should be skeptical mathematically. Okay, so now let's look at example 4. If I were to just hand you this graph and ask you what function this is a graph of, I hope you would tell me it's the sine function. Okay, it starts at 0, 0, it's got an amplitude of 1. This should be, for all intents and purposes, it should be the sine function. But I am asking you to write me an equation for this using the cosine function. Okay, the plot thickens here. If this were the cosine function, think about where this point would be, and pause the video if you need to, but think about where this point would be. If this was the original cosine function, the top of that bump would be right here. Okay, so the movement that I did was from here over to here, if I wanted to think of this as a cosine function that's been translated around. That's a shift to the right by pi over 2. So the translation that I did to the cosine function would have been a positive pi over 2. I didn't vertically shift it at all. I took my cosine function, I dragged it to the right by pi over 2. So if I want to write the equation as a cosine function, I would say cosine of x minus pi over 2. Okay? There is a distance of pi over 2 between the sine function and the cosine function. So let me convince you of that using Desmos here for a second. Get rid of all our ugly tangents. Okay. Let me give you the sine function. Okay. Let me give you the cosine function. So what I just did is I wrote an equation for the black function by translating the blue function. I took this point here and I dragged it over to here. Okay, I dragged it by a distance of pi over 2. So if I wrote that equation in here, y equals cosine of, what did we say, x minus pi over 2. Notice that green function looks exactly like the original sine function. Okay, that's an important relationship to know, and that's related back to that complements theorem that we talked about, where the sine of pi over 2 minus x is the same as the cosine of the original x, and vice versa. We talked about that in the last section, that the sine and cosine are always off from each other by a factor of pi over 2. I think that's it on translations. I really think the translations are probably easier than the scale change ones are. What you have to look forward to now is the next lesson gets into us doing both things at the same time. It's super fun. But that should be enough to get you through lesson 4.8. So thanks for listening, and I hope you have a great day.